Hello everyone, welcome to Chip Confessions. In our previous session, we saw about types of assignments in Verilog, that is procedural and continuous assignments, and in this session we will be looking about scheduling semantics in Verilog. So I will be dividing this session into two parts. In the first part, we will be seeing about how the simulator is going to execute a Verilog code, and in the next session we will be looking into detail about the scheduling regions. So as I said, how the simulator is going to execute the code means we have a language called Verilog, which is a hardware description language, and in this code, whenever we write a Verilog code, we will be having multiple blocks. As I said, we will be having initial block, always block, or we will be having continuous assignments also with the assign keyword. Like that, we will be having many such blocks in the code. And what we have to keep it in mind is whenever we are running this code, we should know that these blocks will run in a concurrent way. Means multiple initial block will start executing at the 0 simulation time, whereas multiple always blocks will be there. Those can also run at 0 simulation time if there is no sensitivity list, or based on the sensitivity list they can also get start getting executed. Like that it happens means we will be having multiple blocks of code which can run in a concurrent way. So we have to take into consideration that the execution should happen in a smooth way and it should not clash with any other statements while executing. That clash is nothing but what we call as race around condition, where a simulator cannot decide what value it has to assign to a signal or how to resolve that clash, which can end up with a deadlock kind of situation. So in normal software languages such as C or C++ or Python, the thing is those code will run in a sequential way where concurrency is not present. But Verilog is not like that. We have concurrency here. So to make that concurrency to happen in a smooth way, this Verilog language has got something called as event scheduler. What is this event scheduler? Event scheduler means it will define how and when the code or the blocks in the code should get executed. Means that scheduler will divide the time slot into multiple regions so that the code execution can happen in a smooth way without any clashes in between. We shall see how it happens. So we have a simulator and this will be executing the code which is written in Verilog. So basically we have a Verilog simulator executing Verilog code. Consider okay, before this we need to know few keywords actually. One is the event, next is the time step or time slot, and next is the event. We need to know about all this. As I told, the simulator will start executing the code. How it executes? We have something called as event. What is this event? As I said in one of our previous videos, event is nothing but an change, an update, or a change in a signal. Means whenever there is a change or update in the signal, it is called as an event. Means there should be some change which can be considered as an event. Event is nothing but a change. And then we have time step or a time slot. What is this time step or a time slot? This time step or a time slot is nothing but the simulation time. Means whenever we are executing the code, the simulator has a virtual clock which is running. That time or the moment of time in that virtual clock is nothing but your time step or time slot. Means time step or a time slot is nothing but part or a moment of your simulation time. For example, if I say we have an initial block which is running or which starts executing at 0 time unit. That 0 time unit is nothing but your time step or a time slot, which is a simulation time or a part of your simulation time. So this time step or time slot is nothing but a part of your simulation time. Then we have something called as event queue. What is this event queue? Means before that we should know something called as the type of simulator, which is majorly we have two types, which is event driven and cycle driven. What is this event driven or cycle driven simulators? These are the two major types of simulator. What happens in event driven simulator? In event driven simulator, the changes in the signal, any change in the signal will be considered as event. So whenever we are running a code and any changes in the signal happening in that code will be considered as an event, and we can give delays here and we can give any explicit event declaration here. Means whatever the changes in the code or whatever the time delays we are giving, everything will be considered in the form of event. So it is called as event driven simulator, and this is a complex type of simulator because it has to take care of each and every changes in the signal which is happening during the simulation, and this is used to verify most complex designs where the changes in the signal, means in between changes in the signal is important, and this is slower when compared to this cycle driven because of the increase in the complexity. What is this cycle driven simulator? This cycle driven simulator is nothing but it will just take care of a clock cycle. Means there should be a reference clock, and based on this clock for each cycle only once the signal will be checked. For example, we have a signal A, and the signal value of the signal A will be checked only once per clock cycle, and whenever if the clock or if the signal A, value of signal A is changing in between, then that won't be taken into consideration. Means once in a clock cycle, wherever we mention like posits or negates, like that if we mention, at that particular point of time only the signal value will be checked, or the the changes in the signal will be considered. But if the changes in the signal is happening beyond that point of time, that changes will not be considered. So this will be linear kind of. Means for example, if we have a clock, as I told, for every cycle only once it is checked and it is linear, and in between it will not be caring about any other changes happening with respect to the signal we defined in our code. But in event driven it is not like that, and this event driven can also consider with respect to the clock cycle also and with respect to the event also. Means for example, if we include a clock, then based on this posits or negates we can check whether the signal is changing or not, or whether any execution or any update is happening or not. But it is not mandatory to have a clock in event driven. But in cycle driven, the clock, the reference clock is must, and in cycle driven we can't verify asynchronous designs, because in asynchronous designs it will be independent of clock and signal values will be updated in between any point of time. So it is not possible to verify asynchronous type of designs in a cycle driven simulator, whereas we can verify both synchronous and asynchronous both. Means the code which is getting executed with respect to the clock and may not be with respect to the clock, both types of codes can be executed in event driven. Basic thing is In event driven simulator, everything, every change will be considered as an event, whereas in cycle driven simulator, one reference clock will be there, and for each cycle only once the signal value will be set. This is what the type of simulator is. Okay, and for your whatever we use like model sim, Questa sim, or Synopsys VCS, or Cadence NSYSIM, those things, everything is event driven only. Okay, so that we will not miss any of the an update of for a signal which is happening while executing the code. So as I said, whatever the simulator we use that is event driven means whatever the changes which is happening in the code while executing, whatever the changes which is happening for a signal during the execution of the code will be considered as an event. And there may be series of changes, like if a code is changing at 0 time unit, may change even at 2 time units. For example, the time unit is nanosecond here. If we consider like this, at 0 nanosecond, for example, signal A is taking the value of 1, and at 2 nanosecond signal A may become 0, and something at 10 nanosecond the signal A may change its value to 1 again. So this event is nothing but this series it will take, means for 0 nanosecond there will be an event, 2 nanosecond there will be an event, and at 10 nanosecond also there will be an event, and these events together will be called as event queue. So whenever we have a code, and that code if we start running or start executing, initially what happens is the compile of the code, and that compiler will compile the code, and once it is compiled then it will start running. Means if all the syntax everything is cleared and if everything is clean, then it will start running the code. At that time this event queue will be having the events, current event and the future events, means it will not have all the events. Like for example, if the signal A is changing for 100 times in the code, means this event queue will not be having 100 number of entries at the beginning itself. It is like this event 0 nanoseconds is executed, then the next event it will look, means 2 nanosecond it will take care of, and then next event it will look for. Like that it happens. So event queue will contain the list of future events. Doesn't mean that all the events will be there, no, just one after the other, like that. As soon as the next future event, that will be contained in this event queue. So this is about event, time step or time slot, and event queue. This 0 nanosecond, 2 nanosecond, 10 nanosecond is nothing but your time step or time slot. It is a part or a moment of your simulation time. Okay. Next, what we have to see is, how this time slot is executed. Means if we are telling time slot like 0 nanoseconds, and then we have 2 nanoseconds, and then we have 10 nanoseconds, this means the simulator will not be like 0, 1, 2, and then 3, 4, 5, 6, 7, 8, 9, and then 10. It will not advance its time like this. As it is event driven or event based simulator, it will start advancing its execution based on its events only. Like it will not advance the simulation time like 0, 1, 2, 3, 4 like that in a sequential or linear way. Instead it will advance based on the event time. For example, we have an event at 0. Next, if we do not have anything at 1, it will discard this 1. Then it will go at 2. Then if we do not have anything from 3 to 9, it will discard this complete time slots, and then it will go to 10. So the execution of this code based on the event happens like this. It will not be in a linear way like 0 to end of the simulation at one time units. No. Based on the events, whenever the event is getting scheduled, at that time only the simulation will run. For example, if we have an initial block, it is executing at 0 nanosecond, then we are calling some $finish to finish the execution at 50 nanosecond. It means from at 0 nanosecond something got executed, from 1 nanosecond to 49 nanosecond we do not have anything, nothing will be there, no event will be scheduled. So what the simulator will do after the 0 nanosecond execution, directly it will jump in 50 nanoseconds and then it calls for the finish and the simulation will be completed. It is like that. So we need to understand how the time advances in simulator. Like you can think like we will be having 0 nanosecond and 1 nanosecond, we are declaring like that in time scale. As I mentioned in one of our previous sessions, we'll be having something called as time scale. This time scale will define the time unit on which unit your simulation time has to consider. We will be having nanoseconds, or we will be having seconds, or we will be having milliseconds, we will be having microseconds, like that it will be there. Usually by default is nanosecond. Okay, this will be there, and when the simulator starts running the code, you can think of like everything will happen in nanoseconds only. Means in time scale as we defined in nanoseconds, the simulation may happen in nanosecond. Like that, if you think, it will not happen like that, because this simulation time is different from whatever the time we have in our real world. For example, a simulation, even though if we are running in nanoseconds and if even though we are calling $finish at 20 nanoseconds, we can think like this is happening at 20 nanoseconds only, because for example we have a code. Okay, we can consider a code where we have initial block, and then inside this initial block we will be having some code which has got at 1 nanosecond I am updating signal A with, and then next we will be calling at 10 nanosecond I am calling dollar. So this is the code we have, some crude code I have written. Okay, we have an initial block there at 1 nanosecond. Let us consider the time scale as 1 nanosecond, and we are running this code, and at 1 nanosecond A is taking the value of 1, and at 10 nanosecond we are calling finish, so that to end the simulation. You can think everything will be finished within this 10 nanosecond, because at this point of time, before calling this $finish, if you say 10 nanoseconds and directly calling $finish here, if you display the time, this will be 10 nanoseconds only. This will be 10 nanoseconds only. But and here if you display, it will be 1 nanosecond only. And in between, wherever you display the time, it will be 1 nanosecond only. And at last, as you are giving this 10, this will be 11 actually, because 1 plus 10, 1 will be added. So this will be 11 nanoseconds, because this 1 nanosecond delay already happened, and this will be added with this 1 nanosecond, and here we will get 11 nanoseconds as time. So here what happens in between this 1 nanosecond and 10 nanosecond, no matter wherever you display the time unit, it will be 1 nanosecond only. And here if you give, it will just come to 11 nanosecond. You can think how this jump happened. It is because as I said before, this is event driven. based on the event only the simulator will advance its time, advance its simulation time. And this is different from whatever the time we have in real world. Means if you check after running this code, if you check, there will be something called as total simulation time, and it will be showing in some seconds. Say it is 1 second or 10 seconds, like that it will be showing. And you may find it little surprising, even though you have given everything in nanosecond, how much, why it took seconds to execute the code. But the real time or the real world clock, whatever the time it shows, will be different from the simulator time. This we will look or consider in a deeper way when we go to the scheduling regions. What you have to understand is the simulator will be having its own virtual clock which runs the simulation time, and it will be based on your choice. Means it can be nanosecond, or it can be your picoseconds, or it can be microsecond, millisecond, or normal seconds also. You can give like that. That is your choice. How your simulator or how your code demands, like that you can give. Based on that, your simulator will adjust its virtual simulation clock. But even though you have given in seconds, for example, if I say here I have given 1 second, here I have waited for 10 seconds, and here if I print it will be 11 seconds, but when you run the code it will show 1 second only. That possibility is also there. So we have to understand, whenever we are running a code, we have a virtual clock which will be running or which will be controlling the simulation time, and whatever the clock we have in the real world, that is different. And based on the complexity of the design, simulation time may increase or decrease. Means whenever you are running a simple AND gate, the simulation time may be less than a second, and whenever you are running millions of AND gates together, the simulation take more than a day or sometimes a week. Like that. Means depending on the complexity of your code, the simulation time vary. Even though you have given in nanoseconds in a code where you have written millions of AND gates, the simulation time may be in days, even though you have given in nanoseconds. Your time scale defines in nanoseconds, but your real time of execution is taken in days, that is multiple or hundreds of hours. So there is a difference between the simulation time and the real world or real clock time, that you have to keep it in mind. So today in this session what we saw is how the simulator executes the code, and we saw the type of the simulators, that is event driven and clock driven cycle driven simulators. And we also saw what is an event, what is an event queue, and what is a time step or time slot. We will just refresh them in brief in less than a minute in our next session, and we shall see into deep why those regions we saw today, like why those scheduling regions are required, because we will be running the code in a consistent way in Verilog. To avoid that clashing of those things, we just made, or the IEEE standard made the regions so that it has specified which block of code or which line of code has to get executed in which regions, and those regions we will be seeing in our next session with the help of the code. So this is for today's session, and if you have any doubts you can put in the comment box below. Next session. Thank you for watching this video. Please like, share video, and then subscribe to my channel. Update. Thank you so much.